Welcome back, dear grade 9 students. In this video, we are going to talk about the tangent to a circle. So, what is a tangent? A tangent to a circle, as you see here, intersects it at only one point or contacts it at only one point. That's called the point of tangency. When the tangent is perpendicular to the radius or the diameter at that point of tangency, and as you notice, the distance from the center to that line is exactly equal to the radius. So how to prove a tangent? How to prove that a line is a tangent in a certain circle? To prove that a line is a tangent to a certain circle, we have to prove first of all that it is perpendicular. There is a right angle between the line and the radius at the point of tangency, and we have to mention that the distance from this center to that line is exactly equal to the radius, and it's written like d means the distance, parenthesis, from O, the center, to that line, t, we call it usually t, is equal exactly to the radius. That's to make sure that not any perpendicular to the radius is a tangent. It may be here, but a tangent must be a perpendicular to the radius, and it must be contacting the circle here at that one point. That's called the point of tangency. So the distance from that center to that point is exactly equal to the radius, not more nor less. And now we are going to talk about a new property that's called the property of two tangents to the same circle from an exterior point. So here we have a circle, and here are two tangents from an exterior point called M. That exterior point has two tangents to the circle. One of them intersects the circle at the point of tangency D, and the other intersects the circle at the point of tangency E. So we have to discover a property using the congruent triangles. Using the proof of congruent triangles, we have to prove that triangle MOD and triangle MOE are congruent, and then by naming the homologous elements we can deduce the property. Now let me remind you of something concerning right triangles. To prove right triangles congruent, we can maintain that they have equal hypotenuse. Okay, as you see here, MO, for example, is a common hypotenuse, then definitely it's equal in this triangle and in this triangle. So we have to maintain the hypotenuse, and we can search for either an angle or a side. Let me explain. So when I maintain that the hypotenuse is equal, then I can find if this angle is equal to this angle, then these two triangles are directly congruent. That's a property only in a right triangle. Or if this side equals to this side, or if that side equals to that side, any side from this triangle and any side from this triangle. If I maintain the hypotenuse and any side in the two triangles, or any angle, for example this or these, we can directly say that these triangles are congruent, and that has a proof that we can talk about later, but you can use it now as a property. So you can prove right triangles congruent by using hypotenuse side or hypotenuse and angle. And now let's apply that idea I'm talking about in this triangle, in these triangles. First of all, we have to say that MO is a common hypotenuse. These triangles are right. We have to mention that. MO is a common hypotenuse. OE and OD are the sides we are going to use, because we cannot know anything about angles here. We don't have any idea about angles, but we have idea about radii, because OD and OE are radii. They are equal, so we can maintain equal sides from this triangle and this triangle, and thus triangle MOD is congruent to triangle MOE by HS. So we used here the idea of H means hypotenuse and S means a side from this triangle is equal to side from this triangle. Now, to name the homologous elements, so all what we have to do is to mention them. The homologous elements are, this side is going to be equal to this side, this angle here is equal to this angle here, and this angle here is equal to this angle here. So these are the homologous elements of these two congruent triangles. Now let's write it in a clear way. So if we have a circle and an exterior point, these are two tangents issued from this exterior point. Here are the points of tangency, and here are the right angles that are made by the radii and the tangents. We can conclude that directly, and we can use it as a property without any proof, that MD, that distance, is equal to ME, and that angle MOD is equal to MOE, as you see. So MOD is equal to MOE, and OMD is equal to OME. So as if we are saying that that line MO, if we extend it, that line MO is an axis of symmetry for the figure. If we fold the figure along that axis of symmetry, we can notice that MD will coincide with ME. This angle will coincide with this, and this will coincide with this. So we can conclude that the line joining the exterior point with the center is considered as an axis of symmetry. That means if we join D and E, that chord, we can deduce that MO is the perpendicular bisector of that chord DE, and it's the bisector of angle DME and DOE. So that's a property of the line joining the center and the exterior point where the two tangents are issued from. Now let's take a training exercise using this idea. Here is a figure, and here we have that A is symmetric of D with respect to M, so we can conclude that M is a midpoint of DA. AD and ME are given two tangents, so AD and ME, as you see here, are two tangents. We can say that MD and ME are also two tangents starting from the same point M. So what's the nature of triangle DEA? Let's think a little bit. What's the nature of triangle DEA? It seems to be a right triangle at E. So right, it seems to be a right triangle at E. So again, the given is that A is symmetric of D with respect to M. What does that mean? That means that M is the midpoint of DA, as I mentioned before. And we have that MD and ME, if AD is a tangent, then directly MD is a tangent also. So MD and ME are two tangents to that circle from the exterior point M. So we have to control them from M here. Now definitely MD is gonna be equal to ME, and that's the property of two tangents to the same circle. So we have now that MD is equal to ME. What do we have to do with the symmetry? Symmetry says that MA is equal to MD also by symmetry. So since M is the midpoint by symmetry, then MD and MA are equal. Then by comparison, what are we going to get? MD equals ME, MD equals MA, then by comparison we can get that these three parts are equal, MD, ME, and MA. And that's the converse of the median property relative to the hypotenuse in a right triangle, and thus E is right, and thus triangle DEA is a right triangle at E. So let's see the proof. DM equals ME, that's property of tangents to the same circle from an exterior point. DM equals MA by symmetry, then by comparison DM, ME, and MA are equal. So DEA is a right triangle at E, and that's called the converse of the median property relative, the converse of the property of the median relative to the hypotenuse in a right triangle. So if you remember, in any right triangle, we have that the median, because M is midpoint of the hypotenuse, we have that the median relative to the hypotenuse is equal to half of it. So these pieces are equal. And conversely, whenever we have these pieces equal, then we can conclude that this triangle is right and DA is its hypotenuse.